Hey everyone, um, welcome back. Welcome back to my live stream. Please let me know if I am not audible. I hope I am. Let me just test it once. Um, if I was audible.
And I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we are going to start with a blank Jupyter notebook. Hello, my name is Andrej, and I've been... Hello, my name...
Okay, so all of you know I have been trying to learn several things, but yeah, I'm caught up with my workload and a lot of other commitments, and not able to make time for the YouTube channel, and also not able to make time for my own learning. I feel stagnant if I'm not learning something new, but yeah, I'm making conscious effort to keep myself accountable, and I want to hold myself accountable and start learning. So today I have come here, not much plan, nothing, but I'm gonna sit here and learn something. So we had looked into Andrej Karpathy's the same video, the spelled out intro to neural networks and back propagation, but it's been a while. I have lost touch, so I want to repeat it and go through the video once and get the concepts clear in my mind. And at the same time, if somebody else wants to learn with me, it's a great opportunity for me as well as you, and um, we can go ahead in the journey together and learn the concepts. Main focus is nothing flashy, nothing exuberant plans. Just sit here, learn things, make the basics uh, very clear, and make slow iterations, slow progress, but keep the consistent progress. And I don't want this to be one of the weekends where I come here and just create a live stream and go away, but I want to have a continued consistent learning pattern. So let's do that. I think I was tired of like uh, thinking about preparing for the live stream and then coming up here and then presenting things, but yeah, but it's hard to make time. And I like in trying to make it more better, or um, more like a professional video. uh, Trying to make it like a more professional video, I'm kind of losing the opportunity to even learn. So now my focus is to learn, and then let's see how it goes once I get better at this. Okay, let's get started. And I'll pause the videos in between, and then I'll try to explain what I understand. If someone has a question, feel free to drop a comment in the live stream. I'll make sure to address those comments. If not now, I'll try to address those comments and make a separate video, or in the subsequent live stream, I'll address those. Let's get started from the beginning of the same video. And thanks to Andre for making this, making these videos, which we are made to make the full use of. But thank you very much. It is available for everybody, so I'm just watching that video now.
My name is Andrej, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to... Hello, my name is Andrej, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we are going to start with a blank Jupyter notebook, and by the end of this lecture, we will define and train a neural net. And you'll get to see everything that goes on under the hood and exactly sort of how that works on an intuitive level. Now, specifically what I would like to do is I would like to take you through building of micrograd. Now, micrograd is this library that I released on GitHub about 2 years ago, but at the time I only uploaded the source code, and you'd have to go in by yourself and really figure out how it works. So in this lecture, I will take you through it step by step and kind of comment on all the pieces of it. So what is micrograd and why is it interesting? Good. Micrograd is basically an autograd engine. Autograd is short for automatic gradient. And really what it does is it implements backpropagation. Now, backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality of micrograd is, I think, best illustrated by an example. So if we just scroll down here, you'll see that micrograd basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are -4 and 2, but we are wrapping those values into this value object that we are going to build out as part of micrograd. So this value object will wrap the numbers themselves. And then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of micrograd and the operations that it supports. So you can add two value objects, you can multiply them, you can raise them. Hello, my name is Andrej, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we are going to start with a blank Jupyter notebook, and by the end of this lecture, we will define and train a neural net. And you'll get to see everything that goes on under the hood and exactly sort of how that works on an intuitive level. Now, specifically what I would like to do is I would like to take you through building of micrograd. Now, micrograd is this library that I released on GitHub about 2 years ago, but at the time I only uploaded the source code, and you'd have to go in by yourself and really figure out how it works. So in this lecture, I will take you through it step by step and kind of comment on all the pieces of it. So what is micrograd and why is it interesting? Good. Micrograd is basically an autograd engine. Autograd is short for automatic gradient. And really what it does is it implements backpropagation. Now, backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality of micrograd is, I think, best illustrated by an example. So if we just scroll down here, you'll see that micrograd basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are -4 and 2, but we are wrapping those values into this value object that we are going to build out as part of micrograd. So this value object will wrap the numbers themselves. And then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of micrograd and the operations that it supports. So you can add two value objects, you can multiply them, you can raise them to a constant power, you can offset by 1, negate, squash at 0, square, divide by a constant, divide by it, etc. And so we're building out an expression graph with these two inputs A and B, and we're creating an output value of G. And micrograd will, in the background, build out this entire mathematical expression. So it will, for example, know that C is also a value. C was a result of an addition operation, and the child nodes of C are A and B, because and it will maintain pointers to A and B value objects. So we'll basically know exactly how all of this is laid out. And then not only can we do what we call the forward pass, where we actually look at the value of G, of course, that's pretty straightforward. We will access that using the .data attribute. And so the output of the forward pass, the value of G, is 24.7, it turns out. But the big deal is that we can also take this G value object and we can call .backward. And this will basically initialize backpropagation at the node G. And what backpropagation is going to do is it's going to start at G, and it's going to go backwards through that expression graph, and it's going to recursively apply the chain rule from calculus. And what that allows us to do then is we're going to evaluate basically the derivative of G with respect to all the internal nodes, like E, D, and C, but also with respect to the inputs A and B. And then we can actually query this derivative of G with respect to A. For example, that's A.grad. In this case, it happens to be 138. And the derivative of G with respect to B, which also happens to be here, 645. And this derivative, we'll see soon, is very important information because it's telling us how A and B are affecting G through this mathematical expression. So in particular, A.grad is 138. So if we slightly nudge A and make it slightly larger, 138 is telling us that G will grow, and the slope of that growth is going to be 138. And the slope of growth of B is going to be 645. So that's going to tell us about how G will respond if A and B get tweaked a tiny amount in a positive direction. Okay. Now, you might be confused about what this expression is that we built out here. And this expression, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly bit less crazy even. Neural networks are just a mathematical expression. They take the input data as an input.
Okay, until now, whatever Andre explained mainly is about the micrograd tool. So I'm still not sure if micrograd is like a very popular or well-known tool that is being used with neural networks extensively, or is it it is something that Andre has built for his own convenience to explain the concepts. So here, as he mentioned, he was just flexing about all the operations that micrograd supports and everything that can be represented. And also he touched upon like the forward pass and the backward operation here. Um, and also he mentioned gradient a couple of times, but yeah, he hasn't explained any of those conceptually. So let's wait for some more time with patience and follow the video in order to see if he will explain all those concepts in the from the basics. Otherwise, what I'll do is I'll only explore about the terminologies that he mentions, and we'll try to get the basic details of those. For now, let's wait. I think he's starting with the known terminologies of what is neural networks now, and he might get to those other topics in the meantime. Okay, let's continue the video.
And they take the weights of a neural network as an, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly bit less crazy even. Neural networks are just a mathematical expression. They take the input data as an input, and they take the weights of a neural network as an input. And it's a mathematical expression, and the output are your predictions of your neural net or the loss function. We'll see this in a bit.
Okay, yeah, as he mentions, neural network is consists of like the inputs and then the weights, and then that combination of the input and weights will provide us the output. or the predictions basically, and how it is computed or how it will look in detail, we can, I think, see further in the video.
But basically, neural networks just happen to be a certain class of mathematical expressions. But backpropagation is actually significantly more general. It doesn't actually care about neural networks at all. It only cares about arbitrary mathematical expressions. And then we happen to use that machinery for training of neural networks. Now, one more note I would like to make at this stage is that, as you see here, micrograd is a scalar-valued autograd engine. So it's working on the level of individual scalars like -4 and 2. And we're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times, and it's just excessive. And so obviously you would never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations on those large arrays that allows us to take advantage of the parallelism in a computer. And all those operations can be done in parallel, and then the whole thing runs faster. But really none of the math changes, and that's done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And I think
Okay, now I think there is a now I think there is a overload of a lot of terminologies. Let's keep track of those, like what we need to follow. I think he mentioned about forward pass, so let's see if we will understand that. And then there is backward method, I guess, or he mentioned backward propagation. I think let's keep it at it. And also he mentioned neural networks. I think he provided good enough context about neural networks, but yeah, we can see it in detail. And also he mentioned about tensors. As of now, tensors are, like he mentioned, tensors are something like a data structures for machine learning to come for performing these operations. But let's look at those things in detail.
And that's why I fundamentally wrote micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later. Okay, so here's the fun part. My claim is that micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that micrograd would be a very complex piece of code, and that turns out to not be the case. So if we just go to micrograd, and you'll see that there's only 2 files here in micrograd. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of micrograd. So engine and nn.py.
Okay, let's focus on this part now. Like he has been explaining how he has built the tool micrograd and neural networks. Basically, as he claims, these are the only things which are needed to train the neural networks, but everything else is efficiency, basically to improve the efficiency. But yeah, but let's look into this one. This might be good enough for us to understand all the concepts that are involved. And it looks like it's a very simplified version. Like as he explains, the engine.py is very small file, and then nn.py also is a file where we can read each and every line of code and see what it's doing. I think Andrej will explain it in the video now. Let's hear it from him.
So the actual backpropagation autograd engine that gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons. And so it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code. And that's all you need to understand neural network training, and everything else is just efficiency. And of course, there's a lot to efficiency, but fundamentally that's all that's happening. Okay, so now let's dive right in and implement micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic imports that I copy paste in every Jupyter notebook always. And let's define a function, a scalar valued function.
He's talking about Jupyter networks and Jupyter notebooks and how he will visualize the data and how he will run that code and all that. So first thing, okay, micrograd is the tool which is used to run these operations, and there's going to be much more details about it as he explains in this video, as we move forward in this video. First of all, let me talk about Jupyter. So let's look at it together, like what are Jupyter notebooks are. Is it better here? I think, yeah, I think we can depend on Gemini. Jupyter notebooks. Okay. Let's see. What is Jupyter notebook used for? A Jupyter notebook is used for data science, including cleaning and transforming data, exploring data sets, and building machine learning models. It allows users to create and share documents with live code, equations, visualizations, and narrative text, making it ideal for creating living documents for analysis tutorials and executable documentation. Okay, makes sense. Basically, I think we need to assume this one. A Jupyter notebook is used for data science, including cleaning and transforming data, exploring data sets, and building machine learning models. That is clear. And how to install Jupyter? I think I use Mac, I use MacBook. So I think I used brew install Jupyter Lab with this command. I think we can install it using pip as well. Yeah, and then Jupyter Notebook. This is the command that we run to get the notebook server running locally. So I have the Jupyter Notebook installed now, and I have the server running. So I have this one, local notebook, and like I just created a new file. This is new interface for me as well. Like I have never used Jupyter in any professional capacity. So yeah, I just created a new file from here, new notebook. This is what I did. Okay, and then yeah, I use the Python 3 kernel that I have installed locally. So for the prerequisite for installing Jupyter notebook is you should have Python running in your computer. Okay. Okay, now like I want to just follow what he does. That's why I have this one open. But yeah, like I think I'll just duplicate this one and I'll follow offline so that I offline means I'll follow on another screen apart from what I'm streaming there. So let me duplicate this and pop it out. Okay. And yeah, let's get back to Andrej's video.
F of x as follows. So I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y. And we can call this function, of course, so we can pass in, say, 3.0 and get 20 back. Now, we can also plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola. It's quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25. So x's is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this NumPy array as well. So we get a set of y's if we call f on x's. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get a nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x. right? So what is the derivative at different points x?
Let me pause it here. So I'm not able to follow it. So let me run all those things in my notebook. So this is the notebook we created just now. Okay. We can title it something. What is it we are learning here? Back propagation. Okay. Now let me look into his video, like what he has typed. Okay. Definition f of x. So he's defining a function there. Man, I'm just hitting shift and return. So return 3 power 3 or 3 star x power 2. So that is 3x square minus 4x plus 5. So that's the function. Okay, next one is he's calling the function with the x value as 3.0 and how to execute this one. Okay, definition of f of x, what it says in 3 name error. Okay, name f is not defined. I just defined f of x. Okay, for some reason it's not working for me. I don't know why. I'm so trusted and Python 3. Okay. Okay, first thing is I should get a hang around how to use the Jupyter notebook. So matplotlib inline percentage. What does that mean? That percentage? No module name numpy. Okay, let me start once again. Import math. Import numpy as np and import matplotlib dot pilot as plg and percentage matplotlib inline. Okay. Okay. Okay, let's take the help of ChatGPT to troubleshoot this one since we do not have a lot of time. Okay, here's what I'm doing now. Let me share that screen. Okay, so there's untitled. We can close this untitled. This is the back propagation one. Okay, so let's refresh this one. Okay, this is what we have. And then, yeah, there's a run button, run selected cell. Okay. Okay, still it gives error. So let me see. Hey, I'm trying to execute a Jupyter notebook function. I'm very new to Jupyter notebook as a tool, and also the data analysis and data plotting and all those things. So I don't want to waste it. I don't want to waste a lot of time, or not waste. I didn't have a lot of time to spend to look into the basics of it. Can you help me troubleshoot the error that I'm getting in my Jupyter notebook? Let me share my screen. Are you able to? I'm not sure if you have access to my screen. Can you see my screen?
I can't see. I can't.
What's up with you?
I'm not. I'm not. I'm not. I'm not. I'm not.
Okay, it's funny how this one's behaving. ChatGPT is behaving. Let me see if I can do something else. Okay, so let me just copy paste this one and then see what it gives. I'm not sharing that screen. Let me share that screen as well. Okay, you have got two options. NumPy isn't installed in the kernel you are running. You have got a typo matplotlib.pylot. Okay, matplotlib.pyplot. Sorry. Okay. Yeah, here's the clean fix. Pyplot. Okay, and matplotlib inline. Got it. So import these things. Use the interpreter that notebook or kernel actually uses. Okay, let's just try to get this one. I have the basics. First thing, matplotlib basics typo. So let me compare it with what I had. So, okay, what did Andre had? Matplotlib.pyplot. Okay, matplotlib.pyplot it is. Okay, so at least one thing should be out of the way now. Okay, type.lib inline. So module not found error. Cell 9, line 2. Okay, numpy is not found. So let's do that one as well. The other thing that that was suggested. Let's go to the terminal and see. Okay, here I'm running the Jupyter notebook. So that's the log here, log which is shown here. Nice, this is good. Connecting to kernel, saving file. Okay. Okay, let me open a new tab. Okay, so what we need to do, as I was suggested, let's run to install. Okay, I think I might have three. Okay, externally managed environment. This environment is externally managed to install Python package system-wide. Try view bro install. Okay, or else we can use this one, Python 3 pip install something. So what all we need to install? First is numpy. Let's install it one by one. Use a Python virtual environment, Python 3 pip install. Let's see what does it show for Python 3. Okay, it's not a problem with Python 3. Okay, what's happening here? Homebrew marks its Python as externally managed, so pip won't touch its side packages. Don't fight it, use a virtual environment or Conda and move on. Here are your same options, rank per project virtual environment. Okay, Python 3 m vnv. Okay, there's a homebrew managed packages as well, so let's try that one. Okay, still I have the same error here. So let's see what next. No module name numpy. It's the same error, right? Module not found error. So what's the next option? Okay, last attempt, otherwise I'll just go from basic. Got it. Let's see here. Let's have a refresh. And I have Python Learn AI as the project selected. And then now let's try to run this one. Nice. I don't find anything erroring out. Let's move on to the next function now. Let's define this one. Okay, definition f of x return 3x square minus 4x plus 5. Okay. Definition f of x. Okay. So that should return 3 star x power 2, that is 3x square, minus 4 star x plus 5. And then next one, I'm just calling f of 3 like what he did, basically f of 3.0. Okay. Okay, I might not be sharing the right screen now. Let me share what I'm doing here. Okay. So minus 5 and f of 3.0, and let's run this one. First of all, let's run this one, and then now let's run this one. Okay, it returns 20, so no more errors. All I did was like whatever I installed on the CLI there, and then I came here and then I selected that project that I provided as the command line argument. Let me show you that what I did, what I ran there. So basically I ran this command, install it in a virtual environment, and then installed everything that I needed, all the dependencies in that virtual environment. And then I think what this one did was, in that kernel, I just provided the project name for that environment. And then I went there and selected the same project name. So now I executed what Andrej was trying out, and yeah, it gave f of 20. So the next step is basically he's trying to plot something xs is equal to np.arrange and ys is equal to f of xs. Okay, what it is, minus 5, 5.25, minus 5, 5.25. So basically, what I think we can see from this plot, starting from minus 5, x value where is till plus 5 with increments of 0.25. That's what I understand. And y is equal to f of xs. Like for each value of xs, calculate ys and plot it accordingly. Plt.plot xs and ys. Okay, let's do that. Okay, what he has done, xs is equal to what is that command for what? np.arrange. np is numpy np.arrange. Okay, minus 5.0 and up to 5.0 with the increment of 0.25. Okay, and ys is equal to f of xs. F of is nothing but the function that we have defined here, 3x square minus 4x plus 5. And then what we need, f of xs. Yeah, and then he was plotting this one. So for plot, plt.plot xs and ys. Okay. It's saying np is not defined. Okay, no attribute arrange. Okay, it's a single R, I think. Great. So that was a typo there. So now it is plotting the same way as it was plotting there. So I think this was a bit of slight detour into getting accustomed with Jupyter Notebook and those tools. So I did not want to spend a lot of time separately to learn about the basics of Jupyter Notebook or other tools, but I want to make it fun. I think I promise that I'll make it fun and practical oriented, like as we go along, learning along in this journey. But we are still in the basics. Let's not jump the guns and try to hit acceleration, but slowly get the basics right. Let's get the basics right. Once we are with that, we can we can go crazy. We can try to build something crazy and fail or succeed or do whatever, but we will keep learning. That's the thing. In this era of AI, we don't want to be left behind, at least in terms of knowledge. In other things, it's fine. In terms of knowledge, let's keep up with that one. Okay, let's continue the video.
Of this function. Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write it out on a piece of paper and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. it would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative, we see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by a small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, is 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if we slightly go positively, the function will respond positively. So use the derivative, of course. Plot x's and y's, and we get a nice parabola, quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range.
Just retrace it back to listen to it once again.
From -5 to 5 in steps of 0.25. So x's is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on x's. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get a nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative at different points x of this function? Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write out on a piece of paper and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. It would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative, we see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by a small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.
Okay, this is what I really like about his videos and the explanation. Even though it looks like he's going from very high level, I think the fact is he is going in very low level and trying to explain the basics. That feels like high level. let me explain what I think. What does that mean? So basically now, even though we might know what is a derivative and what is differentiation and all those things, we might not think the practical applications of the same thing. So he is kind of giving the intuitive or the most intuitive possible explanation, or trying to make us understand it intuitively, each and every concept that he is explaining. Let's understand it, and I think it's kind of self-explanatory. Let me see what he will explain, and then we can dive deep together.
0.001. And let's say we're interested in point 3.0. So to take and the slope, how does the function respond? Over derivative. We just look up what I'd like to do is I'd like to look at the derivatives. Neural networks actually writes out the product. Back to your calculus class, you've probably, which is here, the y coordinate. So now I'd like to think through what is the.
Okay, hear this out. These are the very important things to get the intuitive understanding of neural networks.
20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative at different points x of this function? Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write out on a piece of paper and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. It would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative, we see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up, you're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, is 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much? Is telling you the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded in a positive direction. And we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope because we have to make h very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer because we're using floating point arithmetic and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it in our head. So 3x squared would be 6x minus 4. And then we plug in x equals 3, so that's 18 minus 4 is 14. So this is correct. So that's at 3. Now, how about the slope at, say, negative 3? What would you expect for the slope? Now, telling the exact value is really hard, but what is the sign of that slope? So at -3, if we slightly go in the positive direction at x, the function would actually go down. And so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay. And at some point here, of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2/3. So at roughly 2/3, that's somewhere here, this derivative would be 0. So basically at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable d that is a function of 3 scalar inputs, a, b, and c. So a, b, and c are some specific values, 3 inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c, and think through again just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point a.
Okay, now I'm a bit overloaded, but I understood the derivative clearly. So he explained like how with what sensitivity the slope will increase or decrease as we increase or decrease the value of x under consideration. So he started with very small values, and then the slope came up to 14. Like basically slope was like the raise overrun. Raise means like what was the difference between the original one and the original f of x and the f of x plus h, the difference between those two, and then what was the increase, that is h. So that would give the slope, which was 14. And now he's computing other things, but yeah, I think I lost my focus there. So let's get back to this one again.
Let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable d that is a function of 3 scalar inputs, a, b, and c. So a, b, and c are some specific values, 3 inputs into our expression graph, and a single output.
Let's come back a little.
Let's look at a bit more complex case. So we're going to start.
Let's come back a little further.
Let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here, slope. So at -3, if we slightly go in the positive direction at x, the function would actually go down. And so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay. And at some point here, of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2/3. So at roughly 2/3, that's somewhere here, this derivative would be 0. So basically at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable d that is a function of 3 scalar inputs, a, b, and c. So a, b, and c are some specific values, 3 inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c, and think through again just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this This is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h, and then we'll get d2 to be the exact same function. And now we're going to print, f1, d1 is d1, d2 is d2, and print slope. So the derivative, or slope, here will be, of course, d2 minus d1 divided h. So d2 minus d1 is how much the function increased when we bumped the specific input that we're interested in by a tiny amount. And this is then normalized by h to get the slope. So yeah, so if I just run this, we're going to print d1, which we know is 4. Now d2 will be bumped, a will be bumped by h. So let's just think through a little bit what d2 will be printed out here. In particular, d1 will be 4. Will d2 be a number slightly greater than 4 or slightly lower than 4? And that's going to tell us the sign of the derivative. So we're bumping a by h. B is -3, c is 10. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but b is a negative number. So if a is slightly more positive, because b is -3, we're actually going to be adding less to d. So you'd actually expect that the value of the function will go down. So let's just see this. Yeah, and so we went from 4 to 3.9996. And that tells you that the slope will be negative, and then will be a negative number because we went down, and then the exact number of slope will be, exact amount of slope is -3. And you can also convince yourself that -3 is the right answer mathematically and analytically, because if you have a times b plus c, and you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of b is -3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b, so if we bump b by a little bit in a positive direction, we'd get different slopes. So what is the influence of b on the output d? So if we bump b by a tiny amount in a positive direction, then because a is positive.
So now if we are nudging the value of b, then like by a little positive direction, that means, or the negative direction. So differentiation of that ab plus c with respect to b is just a. So the slope should be 2. And also, yeah, if we nudge it in the positive direction, then what we are doing, like then the value of, or the product of ab should be slightly more, and when we add c, that should be more. So d2 value should be more. If it is more and more negative, so the d2 value will get to negative. So it will get more negative, or will decrease.
We'll be adding more to d, right? So and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be 2. And why is it 2? Because d of d by db, differentiating with respect to b, would give us a, and the value of a is 2. So that's also working well. And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected, and now c becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher by the exact same amount that we added to c. And so that tells you that the slope is 1.
1 always.
That will be the rate at which d will increase as we scale c. Okay, so we now have some intuitive sense of what this derivative is telling you about the function, and we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to
Okay, now until now, he built up about like how these functions operate at like we just got some hands-on about calculating slope and what is different, what is the differentiation function there and all those things. So now he's moving on to neural networks. So this will be much more important now.
build out this value object that I showed you in the README page of Micrograd. So let me copy paste a skeleton of the first very simple value object. So class value takes a single scalar value that it wraps and keeps track of, and that's it. So we can, for example, do value of 2.0, and then we can look at its content. And Python will internally use the repr function to return this string. Whoops, like that. So this is a value object with data equals 2 that we're creating here. Now what we'd like to do is we'd like to be able to have not just like two values, but we'd like to do a plus b, right? We'd like to add them. So currently you would get an error because Python doesn't know how to add two value objects. So we have to tell it. So here's addition. So you have to basically use these special double underscore methods in Python to define these operators for these objects. So if we call if we use this plus operator, Python will internally call a dot add of b. That's what will happen internally. And so b will be the other, and self will be a. And so we see that what we're going to return is a new value object, and it's just it's going to be wrapping the plus of their data. But remember now, because data is the actual like numbered Python number, so this operator here is just the typical floating point plus addition now. It's not an addition of value objects, and will return a new value. So now a plus b should work, and it should print value of -1, because that's 2 plus minus 3. There we go. Okay, let's now implement multiply, just so we can recreate this expression here. So multiply, I think it won't surprise you, will be fairly similar. So instead of add, we're going to be using mul, and then here, of course, we want to do times. And so now we can create a C value object, which will be 10.0, and now we should be able to do a times b. Well, let's just do a times b first. That's value of -6 now. And by the way, I skipped over this a little bit. Suppose that I didn't have the repr function here. Then it's just that you'll get some kind of an ugly expression. So what repr is doing is it's providing us a way to print out like a nicer looking expression in Python. So we don't just have something cryptic. We actually are, it's value of -6. So this gives us a times, and then this we should now be able to add C to it because we've defined and told the Python how to do mul and add. And so this will basically be equivalent to a dot mul of b, and then this new value object will be dot add of c. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from before. And I believe we can just call them manually as well. There we go. So yeah. Okay, so now what we are missing is the connective tissue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep...
Okay, now we understood like how we have defined the value objects, at least the basic wrapper. Let's define it in our Jupyter notebook and then see. So value object is the one which is like a wrapper on top of the integers, and then here defined the addition multiplication operations within the same class. So let's define here. So what is it? How is it defined? I'm new to Python as well. Class value. Okay. and then he has defined a function init. I think it is like self comma data for that, and then not func, probably it's function. Let's see that one. Definition of init. Okay, and then yeah, makes sense. Okay, so now self.data data, and then how to represent this. So for that he has defined here. So here just return this one, I guess. Yeah, return f of like this. Yeah, so basically value of probably here self.data. Value of self.data. Data is equal to self.data. Okay. Just represent it with all information. And then, okay, now let's test it out. Value of one dot. Repo self. Okay, everything has a self. Okay, value of data of 1. Okay, now let's define add. What do they do? Output. Okay, equal to value of those two. Return output. Okay, let's do this one here. A plus b. Let's define b. B is equal to value of 3 dot o. Okay, and then c is equal to value of minus 10. Let's make it a star b plus c. 2 3 times 6 minus 10 minus 4. Okay, value of minus 4. Perfect. So now he's explaining how to explain that children. So let's get to that concept from the beginning, why he needed that.
We want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So there we go. So
let's hear it out again.
Okay, so now what we are missing is the connective tissue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this _children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children here. So now we can do d.prev, and we'll see that the children of the we now know are this a value of -6 and value of 10. And this, of course, is the value resulting from a times b and the c value, which is 10. Now, the last piece of information we don't know, so we know now the children of every single value, but we don't know what operation created this value.
I did not understand children yet. Let's go back again. Okay.
Yeah. Okay, so now what we are missing is the connective tissue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this _children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children here. So now we can do d.prev, and we'll see that the children of the we now know are this a value of -6 and value of 10. And this, of course, is the value resulting from a times b and the c value, which is 10. Now, the last piece of information we don't know, so we know now the children of every single value, but we don't know what operation created this value. So we need one more element here. Let's call it under.
So d dot value became what? Value of -6 and then value of 10. So when we do d.prev, it is emitting two values. So how are there two values for d.prev? D is a multiplied by b plus c. Okay. So when we do add, self and other. Okay, I wish he explained it a little bit elaborate manner. Basically what's happening is, self.previous, whenever you initiate it, it is initializing it as an empty set. And then when we perform this addition operation is between, okay, before addition we are performing multiplication operation here, a star b. So we a star b, and a value of a is 2 and value of b is -6, and here self comma other, self dot data star other dot data, that is the value value of data value. And then you will have a set where you will have self comma other. Self will be the self value, I guess, and self will be the self value, means value of 2, and other will be the value of 3. So value of 2 and value of 3, but how that's becoming as value of 6 -6, I don't know, but let's see. So now in the full expression d, so that will be a star b plus c. So then the previous value is the current value, which is -6. -6 will be the self and other will be 10. So yeah, got it. So it is like just the previous value and the current value. So that is self and other.
Underscore pop. And by default, this is the empty set for leaves. And then we'll just maintain it here. And now the operation will be just a simple string. And in the case of addition, it's plus. In the case of multiplication, it's times. So now we not just have d.pref, we also have a d.op. And we know that d was produced by an addition of those two values. And so now we have the full mathematical expression, and we're building out this data structure, and we know exactly how each value came to be, by what expression, and from what other values. Now, because these expressions are about to get quite a bit larger, we'd like a way to nicely visualize these expressions that we're building out. So for that, I'm going to copy paste a bunch of.
Okay, let's add that children and operation for getting the previous values and previous operation. So underscore children. Let's implement that also here. Underscore children and underscore operation self dot children is equal to set of nothing, and then self dot op is equal to underscore operation. Okay, and we are not representing in the constructor here, but we are representing both of those in the addition and multiplication operation. So here self comma other, as a tuple it will be, and then operation will be plus, same thing here, and operation will be star here. Okay, and this will be d is equal to, okay, and then what's the shortcut here? Okay, okay, what is that we are missing? Okay, underscore operation is equal to, by default it is nothing. because we are not passing anything here. Okay, we should pass default value for children also. Okay. Now we got the value here. If we want to print this one is marked as previous value, actually not as children there, I guess. Yeah, that's correct, previous value. So it's printing it as previous value. And also the dot operation is this one. Okay, why it's still an empty set, I don't know. Because self.data self and other. I'm adding both self and other. Set of children. Okay, I'm not adding it to the set here. Okay, makes sense.
Slightly scary code that's going to visualize these expression graphs for us. So here's the code, and I'll explain
Now he's trying to visualize the same thing that we defined until now.
it in a bit. But first, let me just show you what this code does. Basically, what it does is it creates a new function drawDot that we can call on some root node, and then it's going to visualize it. So if we call drawDot on D, which is this final value here, that is a times b plus c, it creates something like this. So this is D, and you see that this is a times b, creating an intermediate value, plus c, gives us this output node, D. So that's drawDot of D. And I'm not going to go through this in complete detail. You can take a look at Graphviz and its API. Graphviz is an open source graph visualization software. And what we're doing here is we're building out this graph in Graphviz API. And you can basically see that trace is this helper function that enumerates all of the nodes and edges in the graph. So that just builds a set of all the nodes and edges. And then we iterate through all the nodes and we create special node objects for them in using dot node. And then we also create edges using dot edge. And the only thing that's like slightly tricky here is you'll notice that I basically add these fake nodes, which are these operation nodes. So for example, this node here is just like a plus node. And I create these special op nodes here, and I connect them accordingly. So these nodes, of course, are not actual nodes in the original graph. They're not actually a value object. The only value objects here are the things in squares. Those are actual value objects or representations thereof. And these op nodes are just created in this draw.routine so that it looks nice. Let's also add labels to these graphs just so we know what variables are where. So let's create a special underscore label, or let's just do label equals empty by default and save it in each node. And then here we're going to do label is A, label is B, label is C, and then let's create a special E equals A times B, and E.label will be E. It's kind of naughty. And E will be E plus C, and a D.label will be D. Okay, so nothing really changes. I just added this new E function, a new E variable. And then here, when we are printing this, I'm going to print the label here. So this will be a %s bar, and this will be n.label. And so now we have the label on the left here. So it says A, B creating E, and then E plus C creates D, just like we have it here. And finally, let's make this expression just one layer deeper. So D will not be the final output node. Instead, after D, we are going to create a new value object called F. We're going to start running out of variables soon. F will be -2.0, and its label will, of course, just be F. And then L, capital L, will be the output of our graph. And L will be D times F. Okay? So L will be -8 is the output. So now we don't just draw a D, we draw L. Okay. And somehow the label of L was undefined. Oops. L.label has to be explicitly sort of given to it. There we go. So L is the output. So let's quickly recap what we've done so far. We are able to build out mathematical expressions using only plus and times so far. They are scalar valued along the way, and we can do this forward pass and build out a mathematical expression. So we have multiple inputs here, A, B, C, and F, going into a mathematical expression that produces a single output, L. And this here is visualizing the forward pass. So the output of the forward pass is -8. That's the value. Now, what we'd like to do next is we'd like to run backpropagation. And in backpropagation, we are going to start here at the end, and we're going to reverse and calculate the gradient along all these intermediate values. And really what we're computing for every single value here, we're going to compute the derivative of that node with respect to L. So the derivative of L with respect to L is just 1. And then we're going to derive, what is the derivative of L with respect to F, with respect to D, with respect to C, with respect to E, with respect to B, and with respect to A. And in a neural network setting, you'd be very interested in the derivative of basically this loss function, L, with respect to the weights of a neural network. And here, of course, we have just these variables A, B, C, and F, but some of these will eventually represent the weights of a neural net. And so we'll need to know how those weights are impacting the loss function. So we'll be interested basically in the derivative of the output with respect to some of its leaf nodes. And those leaf nodes will be the weights of the neural net. And the other leaf nodes, of course, will be the data itself. But usually we will not want or use the derivative of the loss function with respect to data because the data is fixed, but the weights will be iterated on using the gradient information. So next we are going to create a variable inside the value class that maintains the derivative of L with respect to that value. And we will call this variable grad. So there's a .data and there's a self.grad, and initially it will be 0. And remember that 0 is basically means no effect. So at initialization, we're assuming that every value does not affect the output, right? Because if the gradient is 0, that means that changing this variable is not changing the loss function. So by default, we assume that the gradient is 0. And then now that we have grad and it's 0.0, we are going to be able to visualize it here after data. So here grad is 0.4f, and this will be in.grad. And now we are going to be showing both the data and the grad initialized at 0. And we are just about getting ready to calculate the backpropagation. And of course, this grad, again, as I mentioned, is representing the derivative of the output, in this case L, with respect to this value. So with respect to, so this is the derivative of L with respect to F, with respect to D, and so on. So let's now fill in those gradients and actually do backpropagation manually. So let's start filling in these gradients and start all the way at the end, as I mentioned.
Okay, this is very important. So now loss function, whatever L that we have calculated, that's the function basically out of the output, whatever we got. So that value, now all we need to calculate is basically how this output gets impacted by the weights or by the other intermediate layers. So how is it useful? First, I'll provide you the context of how it will be useful. So whenever we consider any uh, any machine learning model, that means it's a combination of several weights. So if a data is passed to that machine learning model, it will go through that weights and then provide us the output or the inference. But in order to come up with those weights, there is a machine learning model training process. So in this training process, through this through this continuous training process, the gradient value will be decided, and also the intermediate weights will be decided. So now what he is showing is how the intermediate values or the hidden layers are impacting the final value, and for that he's using the differential functions of loss with respect to the other input layers. This is getting interesting
here. First, we are interested to fill in this gradient here. So what is the derivative of L with respect to L? In other words, if I change L by a tiny amount h, how much does L change? It changes by h. So it's proportional, and therefore the derivative will be 1. We can, of course, measure these or estimate these numerical gradients numerically, just like we've seen before. So if I take this expression and I create a def LOL function here and put this here. Now, the reason I'm creating a gating function LOL here is because I don't want to pollute or mess up the global scope here. This is just kind of like a little staging area. And as you know, in Python, all of these will be local variables to this function. So I'm not changing any of the global scope here. So here, L1 will be L. And then copy pasting this expression, we're going to add a small amount h in, for example, A, right? And this would be measuring the derivative of L with respect to A. So here, this will be L2. And then we want to print that derivative. So print L2 minus L1, which is how much L changed, and then normalize it by h. So this is the rise over run. And we have to be careful because L is a value node, so we actually want its data. So that these...
This is so cool. He explained the basics of derivatives, right? Like before we got to any of these ones, like how the output is impacted based on a particular value. Like in the if we consider the equation as a, b, and c, he showed us like how the total value is impacted by if a is varied. I mean, if a is varied by a small value, higher the value, or incremented by a small value, or decremented by a small value. In the same way, how it will impact if b is incremented or decremented by a small value. Now he's computing the same thing for the bigger functions, or here for L. So now we are calculating, so that's the gradient. We are computing the gradient for A, B, C, D, E, D, F, all of those with respect to L. So the gradient of L with respect to L will be always 0, and always 1 or 0. I'm not sure. Yeah, I think it should be 1, right? L with respect to L, and L minus L. Yeah, L minus L will be 0 actually. Yeah, it will always be 0, but he is computing with respect to the other values. So now with respect to A, in order to compute the gradient with respect to A, he's calculating the here, if you see here. So the value of A is 2 plus h, and h value is a small increment 0.0001, and here the original value is A is 2, and he computed the value of L1, and with A as 2 plus h he computed the value of L2, and now he is doing L2 minus L1 and divided by h. So the slope, how the slope varies with respect to the minor change in the value of A. So that's what he is calculating there. In the same way, he will compute the gradient of all the other variables as well.
These are floats dividing by h, and this should print the derivative of L with respect to A, because A is the one that we bumped a little bit by h. So what is the derivative of L with respect to A? It's 6. Okay, and obviously, if we change L by h, then that would be here effectively. This looks really awkward, but changing L by h, you see the derivative here is 1. That's kind of like the base case of what we are doing here. So basically we can come up here and we can manually set L.grad to 1. This is our manual backpropagation. L.grad is 1, and let's redraw. And we'll see that we filled in grad is 1 for L. We're now going to continue the backpropagation. So let's here look at the derivatives of L with respect to D and F. Let's do D first. So what we are interested in, if I create a markdown on here, is we'd like to know, basically we have that L is D times F, and we'd like to know what is DL by DD. What is that? And if you know your calculus, L is D times F, so what is DL by DD? It would be F. And if you don't believe me, we can also just derive it, because the proof would be fairly straightforward. We go to the definition of the derivative, which is f of x plus h minus f of x divide h, as a limit of h goes to 0 of this kind of expression. So when we have L is D times F, then increasing D by h would give us the output of D plus h times F. That's basically f of x plus h, right? Minus D times F, and then divide h. And symbolically expanding out here, we would have basically D times F plus h times F minus D times F divide h. And then you see how the df minus df cancels, so you're left with h times f divide h, which is f. So in the limit as h goes to 0 of, derivative definition, we just get f in the case of d times f. So symmetrically, dl by df will just be d. So what we have is that f dot grad, we see now, is just the value of d, which is 4. And we see that d dot grad is just the value of f. And so the value of f is -2. So we'll set those manually. Let me erase this markdown node, and then let's redraw what we have. Okay, and let's just make sure that these were correct. So we seem to think that dl by dd is -2, so let's double check. Let me erase this plus h from before. And now we want the derivative with respect to f. So let's just come here when I create f, and let's do a plus h here. And this should print the derivative of L with respect to f, so we expect to see 4. Yeah, and this is 4 up to floating point funkiness. And then dl by dd should be f, which is -2. Grad is -2. So if we, again, come here and we change d dot data plus equals h right here. So we expect, so we've added a little h, and then we see how L changed, and we expect to print -2. There we go. So we've numerically verified. What we're doing here is kind of like an inline gradient check. Gradient check is when we are deriving this like backpropagation and getting the derivative with respect to all the intermediate results. And then numerical gradient is just, estimating it using small step size. Now we're getting to the crux of backpropagation. So this will be the most important node to understand, because if you understand the gradient for this node, you understand all of backpropagation and all of training of neural nets, basically. So we need to derive dl by dc. In other words, the derivative of L with respect to C, because we've computed all these other gradients already. Now we're coming here and we're continuing the backpropagation manually. So we want dl by dc, and then we'll also derive dl by de. Now here's the problem. How do we derive dl by dc? We actually know the derivative L with respect to d, so we know how L is sensitive to d. But how is L sensitive to C? So if we wiggle C, how does that impact L through D? So we know dl by dc, and we also here know how C impacts D. And so just very intuitively, if you know the impact that C is having on D and the impact that D is having on L, then you should be able to somehow put that information together to figure out how C impacts L. And indeed, this is what we can actually do. So in particular, we know, just concentrating on D first, let's look at what is the derivative basically of D with respect to C. So in other words, what is dd by dc? So here we know that d is c times c plus e. That's what we know. And now we're interested in dd by dc. If you just know your calculus again and you remember that differentiating c plus e with respect to c, you know that that gives you 1.0. And we can also go back to the basics and derive this. Because again, we can go to our f of x plus h minus f of x divide by h. That's the definition of a derivative as h goes to 0. And so here, focusing on c and its effect on d, we can basically do the f of x plus h will be c is incremented by h plus e. That's the first evaluation of our function, minus c plus e. And then divide h. And so what is this? Just expanding this out, this will be c plus h plus e minus c minus e divide h. And then you see here how c minus c cancels, e minus e cancels, we're left with h over h, which is 1.0. And so by symmetry also, d by de will be 1.0 as well. So basically the derivative of a sum expression is very simple, and this is the local derivative. So I call this the local derivative because we have the final output value all the way at the end of this graph. And we're now like a small node here. And this is a little plus node. And the little plus node doesn't know anything about the rest of the graph that it's embedded in. All it knows is that it did a plus. It took a C and an E, added them, and created a D. And this plus node also knows the local influence of C on D, or rather the derivative of D with respect to C. And it also knows the derivative of D with respect to E. But that's not what we want. That's just a local derivative. What we actually want is dl by dc. And L is here just one step away. But in a general case, this little plus node could be embedded in like a massive graph. So again, we know how L impacts D, and now we know how C and E impact D. How do we put that information together to arrive dl by dc? And the answer, of course, is the chain rule in calculus. And so I pulled up a chain rule here from Wikipedia, and I'm going to go through this very briefly. So chain rule, Wikipedia sometimes can be very confusing, and calculus can be very confusing. Like, this is the way I learned chain rule, and it was very confusing. Like, what is happening? It's just complicated. So I like this expression much better. If a variable z depends on a variable y, which itself depends on a variable x, then z depends on x as well, obviously, through the intermediate variable y. And in this case, the chain rule is expressed as, if you want dz by dx, then you take the dz by dy and you multiply it by dy by dx. So the chain rule fundamentally is telling you how we chain these derivatives together correctly. So to differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. And there's a nice little intuitive explanation here, which I also think is kind of cute. The chain rule states that knowing the instantaneous rate of change of z with respect to y, and y relative to x allows one to calculate the instantaneous rate of change of z relative to x. as a product of those two rates of change, simply the product of those two. So here's a good one. If a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as a walking man, then the car travels 2 times 4, 8 times as fast as the man. And so this makes it very clear that the correct thing to do, sort of, is to multiply. So car is twice as fast as bicycle, and bicycle is 4 times as fast as man. So the car will be 8 times as fast as the man. And so we can take these intermediate rates of change, if you will, and multiply them together. And that justifies the chain rule intuitively. So have a look at chain rule, but here really what it means for us is there's a very simple recipe for deriving what we want, which is dl by dc. And what we have so far is we know want, and we know what is the impact of d on L. So we know dl by dd, the derivative of L with respect to dd. We know that that's -2.
We know dd
And
by
now,
dt.
because of this local reasoning that we've done here, we know dd by dc. So how does c impact d? And in particular, this is a plus node, so the local derivative is simply 1.0. It's very simple. And so the chain rule tells us that dl by dc, going through this intermediate variable, will just be simply dl by dd times
dd by dt.
dd by dc. That's chain rule. So this is identical to what's happening here, except z is rl, y is rd, and x is rc. So we literally just have to multiply these. And because these local derivatives, like dd by dc, are just 1, we basically just copy over dl by dd, because this is just times 1. So what is it? So because dl by dd is -2, what is dl by dc? Well, it's the local gradient, 1.0, times dl by dd, which is -2. So literally what a plus node does, you can look at it that way, is it literally just routes the gradient, because the plus node's local derivatives are just 1. And so in the chain rule, 1 times dl by dd is just dl by dd. And so that derivative just gets routed to both c and to e in this case. So basically, we have that e dot grad, or let's start with c, since that's the one we've looked at, is -2 times 1, -2. And in the same way, by symmetry, e dot grad will be -2. That's the claim. So we can set those, we can redraw, and you see how we just assign -2, -2? So this backpropagating signal, which is carrying the information of like what is the derivative of L with respect to all the intermediate nodes, we can imagine it almost like flowing backwards through the graph, and a plus node will simply distribute the derivative to all the leaf nodes, to all the children nodes of it. So this is the claim, and now let's verify it. So let me remove the plus h here from before, and now instead what we want to do is we want to increment c. So c.data will be incremented by h, and when I run this, we expect to see -2. -2. And then of course for e, so e.data plus equals h, and we expect to see -2. Simple. So those are the derivatives of these internal nodes. And now we're going to recurse our way backwards again. And we're again going to apply the chain rule. So here we go, our second application of chain rule, and we will apply it all the way through the graph. We just happen to only have one more node remaining. We have that dl by de, as we have just calculated, is -2. So we know that. So we know the derivative of L with respect to e. And now we want dl by dA, right? And the chain rule is telling us that that's just dl by de
multiplied by
-2 times the local gradient. So what is the local gradient? Basically dE by dA. We have to look at that. So I'm a little times node inside a massive graph, and I only know that I did A times B, and I produced an E. So now what is dE by dA and dE by dB? That's the only thing that I sort of know about. That's my local gradient.
d by dA
So
of B,
because we have that
by
E is A
dA
times
of
B,
A
we're asking what is dE by dA?
is equal to B.
And of course we just did that here. We had a times, so I'm not going to rederive it. But if you want to differentiate this with respect to A, you'll just get B, right? The value of B, which in this case is negative 3.0. So basically we have that dL by dA. Well, let me just do it right here. We have that A dot grad, and we are applying chain rule here, is dL by dE, which we see here is negative 2, times, what is dE by dA?
B.
It's the value of B, which is negative 3. That's it. And then we have B dot grad is again dL by dE, which is negative 2, just the same way, times,
A.
what is dE by
Value of A.
dB? Is the value of A, which is 2.0. That's the value of A. So these are our claimed derivatives. Let's redraw. And we see here that A dot grad turns out to be 6 because that is negative 2 times negative 3. And B dot grad is negative 4 times, is negative 2 times 2, which is negative 4. So those are our claims. Let's delete this and let's verify them. We have A here, A dot data plus equals H. So the claim is that A dot grad is 6. Let's verify. 6. And we have B dot data plus equals H. So nudging B by H and looking at what happens, we claim it's negative 4. And indeed, it's negative 4. Plus minus, again, float, oddness. That's it. That was the manual backpropagation all the way from here to all the leaf nodes. And we've done it piece by piece. And really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output. And then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always. So we just go through and recursively multiply on the local derivatives. And that's what backpropagation is. It's just a recursive application of chain rule backwards through the computation graph. Let's see this power in action just very briefly. What we're going to do is we're going to nudge our inputs to try to make L go up. So in particular, what we're doing is we want A.data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some small step amount. This is the step size. And we don't just want this for B, but also for B, also for C, also for F. Those are leaf nodes, which we usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively. So it should become less negative. It should go up to say negative 6 or something like that. It's hard to tell exactly. And we'd have to rerun the forward pass. So let me just do that here. This would be the forward pass. F would be unchanged. This is effectively the forward pass. And now if we print L.data, we expect, because we nudged all the values, all the inputs in the direction of gradient, we expected a less negative L. We expect it to go up. So maybe it's negative 6 or so. Let's see what happens. Okay, negative 7. And this is basically one step of an optimization that will end up running. And really this gradient just gives us some power because we know how to influence the final outcome. And this will be extremely useful for training neural nets, as we'll soon see. So now I would like to do one more example of manual backpropagation using a bit more complex and useful example. We are going to
Okay, this was was great. This was great. I think we saw the example of like manual back propagation and how he computed the gradient values in a very basic neural network that we can say. Um, and the next part of the video will show the same thing for a little bit complicated neural networks. So let's revise this one. And tomorrow, I think when I start the video, let's execute this back propagation by ourselves and get more acquainted or accustomed with the process, or just let it sink in our brain since it's new. But it was very clear the way he calculated the gradients and ran the back propagation. But yeah, let's start revising with that in the next video, and then let's make progress. Let's see how much of it we covered today. So we were able to watch 53 minutes of it out of 2 hours 25 minutes. It's a progress. I want to get done with this one and understand what is back propagation for good, for like any place or any time when someone mentions back propagation, I should be able to visualize it and be clear with what it is, what's that concept, and how it might impact the inputs and how it might impact the inference or the output layer and everything. So that's the goal. Uh, please feel free to post if you have any questions, or if I haven't covered anything, I'll be covering it in the following video, and I'll try to explain that basic in detail. Okay, let's keep learning. Have a good one.